So let me mention those few technical points that I kept referring to a little bit earlier. Well, first of all, notice that the convergence may or may not occur at the endpoints. That's where the ratio test provides or is handling a limit value of 1. And we know that in that situation we don't have, the ratio test does not give any conclusion. So in each case we'll have to find out what happens separately. So whenever we're analyzing the interval of convergence, we're trying to determine the interval of convergence of a series, after we figured out what the interval of convergence is, or the radius of convergence is, we'll have to analyze separately the two endpoints and find out if the series converges at those endpoints or not. We'll see that some series converge at both endpoints, some series converge on one but not the other, some other series don't converge at any of them. So just recapping, what do we have? On the number line, we always have convergence at the center. Then we're going to have absolute convergence between C minus R and C plus R. We're going to have divergence outside of that interval. And we're going to have a question mark at the endpoints. And that's what we'll have to check every time. Now, another point is, if that limit turns out to be 0, remember in the proof we assumed that the limit had to be greater than 0. That's so that 1 over L would be some number that we could use and we called R. But it turns out you can go through the proof, and actually it's a nice little exercise for you to do that. Go back through the proof and assume that that limit is actually 0, and then notice that in that situation everything still works and the series will turn out to have an infinite radius of convergence. That can happen. It just means that our function will actually be convergence of our power series will be convergent to the value of the function for any value of x with no restrictions whatsoever. This only leaves the situation where we have an expression an plus 1 over an, an absolute value whose limit does not exist. It turns out that even in this situation we can get around all the problems and still prove that the claim is true, namely that the series is going to converge within an interval of convergence and is going to converge there absolutely and is going to diverge outside of the interval. The only thing is that the proof is a little bit more involved. We'll have to do something a little bit different since we don't have a limit to work with. We'll have to come up with something else. But again, that is something possible. Your book gives a very nice proof of this fact, and I definitely encourage you to have a look at it. Alright, so we have constructed this power series. We have seen that they're generalized polynomials. We've figured out where they converge. We'll have to go, of course, through some examples and exercises to find out what those interval of convergence look like in several situations and so on. But now what? Well, what can we do with these functions? Can we actually do, for instance, calculus? Turns out that we can, and this is really the powerful thing about power series. Basically, power series look like polynomial, and as far as calculus is concerned, they behave like polynomials. Okay, so what do I mean by that? So let's say that we have a power series. Let's say this is convergent on some interval of convergence C minus R, C plus R. Then, if I want to compute the derivative of this function, so that means the derivative of the whole series, that will turn out to be equal to what I would get by applying the power rule and the addition rule as if it were a polynomial. So simply take the derivative of each term and add them all up. Of course, we're going to start at 1 because the first term, the one for n equals 0, is just a constant, so the derivative will go away. But we're still going to end up with, notice, with another power series. Okay, so this is quite nice. Now I'm not going to give you the proof of this fact, which is a little bit more technical, more involved, and it's really just a question of checking details in terms of the definition of derivative and so on and so on. So again, I'm going to refer you to the book if you're interested in this proof. Not very enlightening, but again, probably not very surprising. It is very much a power series, looks very much like a polynomial, only it's infinitely long. It turns out that its derivative behaves like a polynomial. And of course, the same thing for integrals. The integral of a power series, that is the integral of something that looks like a polynomial except it's infinitely long, turns out to be given by exactly what we would expect. We're going to integrate each piece as we would with the power rule, and then we're going to have to add a constant. Okay? That k in there is the constant. I'm not using plus c because I've already used c for the center of convergence, but that's the idea. So you're going to integrate each of the terms as if it were a finite sum, and then you're going to add a k at the end as the constant. Okay? So in terms of derivatives and integrals, power series are very, very nice. So guess what? If we can write a series as a power series, then we can integrate and differentiate it very easily just using the power rule. We don't have to do any of those complicated methods of integration. And of course, there is a price to be paid for that. We'll have to write the given function as a power series, and that's what we're going to look in the next topic. Okay. Oh, by the way, both of the series given by the derivative and the integral have the same interval of convergence. So the process of differentiation and integration do not affect the radius of convergence. They might affect, however, what happens at the endpoints. So those endpoints still need to be checked out. But as far as the inside of the interval convergence, everything is fine. So again, this is the really powerful thing about series. If there is one thing that you want to remember about series at all, having to do with calculus, it's this slide that you have in front of you right now. If a function can be written as a power series, then its derivative and integral can be computed as if they were polynomials, just considering they're infinitely long.